So we have our next speaker, Ms. Nilufar Vosugh. The title of her talk is Discrimination of Cognitive, Emotional, and Physical Distractions Based on Functional Connectivity Between Thermal and Physiological Signals During Driving. You have 15 minutes for your talk.
Yes, thank you. In the name of God, I'm Nilufar Vosugh, a master's degree student in biomedical engineering from Tarbiyat Modarres University. Our paper is about discrimination of cognitive, emotional, and physical distraction based on functional connectivity between thermal and physiological signal during driving. In this presentation, I first introduce an overview of the topic in general and review the literature and the data set. Afterwards, we describe the method and finally the results and suggestions. Thousands of traffic accidents incur significant material and human costs. Causes of traffic accidents are divided into three groups: roadway and environmental factors, vehicle factors, and human factors. High ritual is created by a secondary task that deprives drivers of the main task. There are generally two types of distraction for drivers, including physical and mental factors. To understand the importance of distracted driving study, please pay attention to this clip.
A 2-second glance means you miss what really matters. Everything else can wait.
If the driver is distracted even for a few seconds, we see that irreparable events can occur. Then automatic detection distraction is essentially to ensure the safety and well-being of drivers today's world. The first study was in the year 1905 about effect of Viper to driving performance. Then in 1930, effect of radio program was studying about distracted driving for the first time started in 1990 and continue up to now. There are many studies on the detection of drivers' distraction. The best performance for the published data was reported in 2019 using only physiological distraction factors. There is only one study that used all distraction factors that we reported 78.36% accuracy. Some studies have done on real condition data, but driving simulator also have been used to study distractions. We use the published comprehensive data sets. In this data, there are different kinds of physiological and thermal signals that are extracted by different sensors. These data include 68 subjects and three types of distractions: cognitive, emotional, and sensory motor distraction, and data's sampling rate is 1. Various distractions were applied to the loaded drive or loaded sessions while driving. There are other sessions, such as rest or baseline, where drivers listened to light music for 5 minutes. The other session was a practice drive in which people became familiar with simulator, and the relaxing sessions was considered as a non-distraction drive. Each session was divided into 5 phases, and simulator were applied to drivers only in phases 2 and 4. For a closer look, we removed phases 1 and 5 that had no stressors. In this study, prenasal perspiration was extracted using raw thermal video. We also used heart rate, breathing rate, and lane offset because they have a normal distribution. The lane offset was calculated by subtracting the length of the vehicle from the length of the road divided by 2. After recognition, the data and the studies that have been done so far, several questions remains. The last one is the first one is it possible to achieve high accuracy to separate the driver's distraction mode from the normal mode? Number two is does adding functional connectivity feature improve classification accuracy? And the last one, is it possible to distinguish the type of distraction from normal mode with high performance? To answer these questions, we designed this block diagram. In the first step, 4 variables of the driving simulator, heart rate, breathing rate, lane offset, and prenasal were called. Then we normalized them with z-score. We then divided the signals into a 10 seconds window with 90% overlap. Finally, we extracted classic and connectivity features for classification. We used leave one subject out cross validation and calculate the accuracy area under the curve, F1 score, and mean square error to evaluation the performance of the distracted detection system. In this article, we defined 2 types of feature, classic and connectivity. According to, to this taxonomy, which was reported in 2019, functional connectivity was divided into 2 groups, non-directional and directional in the time domain. We also divided the classical feature into 2 categories, structural and statistical, the types of which you can see in the table. We computed grander causality as a directional functional connectivity, and we also calculate variance and Pearson correlation coefficient, dynamic time ramping, and cross correlation between 2 variables as non-directional functional connectivity features. We have 2 time series X and Y. If each of them can influence the other, there is a directional connectivity between them. Grandeur prediction is based on multivariate autoregression model. Grandeur is defined by dividing the logarithm of variance of univariate autoregression model error and by the logarithm of variance of bivariate autoregression error. One of the most important parameters in calculating the grandeur causality coefficient is the order of the model. There are several criteria for selecting these parameters. We used Bayesian information criteria. The maximum model order is in this study was 3, and the model degree with the highest BIC value was considered as the final degree of model. We have 6 grandeur predictions coefficient between heart rate prenasal, breathing rate prenasal, and lane offset prenasal. We also have 3 non-directional connectivity between them. Non-directional features include covariance, Pearson correlation coefficient approximately 1 for breathing rate and prenasal maximum, minimum, and mean of cross correlation vector and dynamic time ramping. In this study, three types of, classification have been used: 2, 3, and 4 classes, which will show the results of each cases in the following. At first, we classify normal and distraction driving based on classic feature. Then we added the functional connectivity features and calculate the system performance. We used the Bayesian classification to achieve a 96.29% accuracy in detecting distractions. We classified two types of cognitive distraction: mathematical question and analysis question, from a no distracted drive, and achieve a 91.95% accuracy. You can see confusion matrix of this classification here. Also, to distinguish four classes of distraction, three types of cognitive, emotional, and sensory motor distraction from normal distribution, from normal driving mode, we achieve an accuracy of 74.22%. We use other classification to comparing results with the Bayesian classification. They are support vector machine and 5 nearest neighborhood. We compared the result of three classification to distinguish the driver's distraction from normal and present the result. The best system performance belong to the SVM classifier. Also, compared to other results, we achieved a high percentages in diagnosing two classes of distraction with all three factors. In this study, we showed that the accuracy of detecting a driving distraction from normal with SVM is 99.89. We were also able to distinguish two different types of cognitive distraction from normal class with 91.95% by using the new connectivity feature set. The result shows that two different types of cognitive question create different mechanisms. The new point of this study is use of functional connectivity features in the time domain between driving variables. These results indicate that there is important and, of course, complementary information on connectivity between facial temporal signal and physiological variable for the diagnosis of distraction. For future work, we can use other probability simulator signals, use frequency domain connectivity features, and finally use raw thermal video to extract informative features. There are also some problem with the simulator. The simulator can only show 3 pages of road space. Subjects may not show their true performance in the simulator, and there is a lack of investigation into the factors of weather condition, sudden traffic, and interaction between drivers in the simulator environment. And a last suggestion is to use an automatic system to warn about the types of distraction detection. These are my references. And thank you for your attention.
Thank you, Ms. Vosugh, for your.
You're welcome.
If there's any question, please raise your hand or write in the chat box. Please go on, Mr. Mirzai. Your voice is not uh, loud. We cannot hear you. Actually.
Uh, can you hear me?
Yes.
Thanks for your presentation. I want to ask about the accuracies you reported on the presentation. The accuracies was about was on the test data set or train data set. I didn't get that.
Test data set, and I use a leave one subject out cross validation, and my accuracy is mean of 68 subject with a leave one subject out.
Mm, okay, thanks.
You're welcome.
Dr. Ghazizadeh, please.
Okay, thank you for the presentation. So, two questions. The first question is, what was your ground truth? So, how did you know if the subject was actually distracted or not? What was how did you measure the ground truth? To have your model predict, you should have known if the subject was actually distracted or not, so you can test your model against the ground truth. How did you obtain your ground truth?
I don't understand what your question.
So you're using, let's say, grandeur causality to predict if the subject was
Yes.
distracted or not, right? So it's two classes, distracted or not distracted. Am I correct?
Okay. Grandeur causality, just future of grandeur causality. Um, the accuracy of the system is by a grandeur causality is very low. Increase the accuracy, but the non-directional connectivity features is very informative, is the most informative than grandeur causality features.
Okay, but my question is more basic. I'm asking, so what you're trying to classify is whether the driver is distracted or not. Is that correct?
Yes, two classes, distracted or not distracted,
Okay.
and
Where did you bring the labels? How did you have the labels for distracted?
okay. In this data set, there are some sessions, normal sessions without stimulus, and cognitive sessions that answer and that question, some question, analytical question, and mathematical question as a cognitive distractor, and drivers send some messages on the telephone, and as a sensory motor distraction, and some questions about emotional, as emotional distraction. And we have two states. Number one, no distracted driving, and we have a relaxed drive and baseline drive and no distracted drive together, and emotional and sensory motor, and cognitive distraction, the state of the distraction drive.
I see. So you assume that if the driver is in the cognitive distraction block, he must be distracted. You assume that if he's, let's say, solving a math problem, he must be distracted, right? So you consider that as a distracted condition and the relaxed driving as a non-distracted condition. Is that correct? I'm not sure if did you hear what I said? Hello? Hello?
Hello.
Did you hear my question?
Yes, but the cognitive factor consists of two different type of question. With were identify with good accuracy these two group of normal driving.
Um, okay, I think I partially understood your paradigm, but I guess since the time is running out, I stop here. Thank you.
You're welcome.
Thank you, Ms. Busu, for your